So, hi everyone, I'm Peter. For those of you who don't know me, I'm a postdoc at the University of Portsmouth in Hampshire, not New Hampshire, and I'm working with Orgrar and Joe Callow and a wide range of other people on extreme coronal line emitters. So, as a brief overview of my talk, I'll first begin on explaining ECLEs themselves and give some context. We've heard a little bit about them earlier on in the week. And then I'll describe some ongoing work I'm doing onto a specific object, AT2018 DYK. Some of you may be familiar with this as well. And then I'll be putting these all in context together as kind of one big ECLE family. And then as we've seen, there's plenty of outstanding questions, and then I'll describe some of those and what we're doing to try and answer them. So ECLEs in general, or extreme coronal line emitters, they're reasonably recently, I suppose 2008 isn't really as recent as it once was. The first one is this rather nondescript SDSS galaxy, and it was first seen in the SDSS optical photometry and then spectroscopically observed a year later. Unfortunately, though, it wasn't actually identified as being interesting until 2008. By that stage, we were already largely post-flare, and it was seen to be decreasing in brightness between these two observations. So we actually know for this object and just this object, because there was coincidental photometry that was only, again, recovered afterwards, that the flare occurred maybe about 6 months before the SDSS optical photometry. Its spectrum, however, as you can see, if I get stuck, is rather interesting for those of you who are familiar with host galaxy spectra, because these very strong iron lines are not commonly seen anywhere. The only time you kind of see these coronal features are in Seyfert AGN, but they tend to be only a few % the line strength of O3, rather in case of the extreme coronal line emitters, hence their name, the lines are much stronger and somewhat dominate the spectrum. And additionally as well, the hydrogen feature in this object is broad, and as we'll see later, that's kind of an indication that this is the residual effect of the TDE that was producing this object. So when you find one interesting object and you go looking for others, you start to find them. So we have a second object, and then in a study of the SDSS DR7, we ended up coincidentally with 7 objects. And if you're playing any sort of conference bingo, none of these are post-starburst galaxies. And of this, using this as a kind of a very rough rate estimate, you get 1 per 100,000 per year per galaxy. That's now somewhat out of date, and as we'll see if you go talk to Joe about his recent work or his poster, and that's been updated, but this is within an order of magnitude estimate. Then if we look at the spectra of all these objects together, and the object I've showed you before is this one, they all do share the similar features where we're seeing coronal lines that kind of distinguish them. Most interestingly as well, some of them will show broad features of hydrogen and helium, as you'd expect from optical TDEs. Most noticeable will be this one here, which is a broad helium-2 feature. And another, again, there's no nice names for these objects, so they're all SDSS. In that case, it's J0748. And then this prompted a whole series of follow-up spectra of these objects. So in black, this is the original SDSS spectra. I know it's quite difficult to see. And then we have follow-up taken in 2013 of the objects. And then my most recent work is trying to get more observations from recent times. And as we can see for 2 of the objects, both this one and this one, the coronal lines are still present after now going 20 years. They're still present. The broad features haven't yet changed, so they're largely consistent and constant with each other. And the other objects we see, the coronal lines have either faded, I'll go for this one, have faded very sharply, in most cases almost entirely. And there's only 2 objects, one object that still shows some iron-7 emission, and a second object that you might be able, if you squint, you might be able to see some iron-7, but it's not very clear. That's the final set of objects. So we already have 2 populations of these objects, those that show variability in their coronal lines and those that don't. And to zoom in on an example of this is our friend SDSS J052 again. The broad hydrogen feature, which was very complex at the time of its SDSS spectrum, is now no longer complex. It's just showing the narrow features, and the broad component has disappeared. And also, as you can see here, the iron-10 line has now vanished completely. And as well, most interestingly, actually, between the SDSS spectra and the initial follow-up in some objects, the O3 line was also seen to be increasing in line strength. Most noticeably, actually, in SDSS J1342, where now the rather large resolution difference is unfortunately due to the pesto spectrum, which isn't the most high resolution. but this is a DESI spectrum. As you can see there, the O3 is increasing at least by an order of magnitude, certainly. And again, the hydrogen feature hasn't really changed there much at all. So in these kind of objects, what's going on? Here's the lovely artist's impression of the TDE. So what we expect happening, the TDE itself is occurring, and there's material in the circumnuclear region of the black hole. And this is being illuminated by the soft X-rays, and that's being reprocessed. And as additionally as well, because there's lots of material around the black hole, you might expect there to be additional reprocessing in the mid-infrared, which we do see in all of these objects, and there'll be bonus points if anybody can work out why that color scheme is the way it is. The two non-variable objects stand out quite clearly here, and the rest of the objects will also see more clearly in color as well. The variable objects show this kind of continual decline. There's no sign of rebrightening in these objects at all, but either in the optical, which I'm not showing here because it doesn't show anything, but these are the kind of wide and mid-infrared colors, where initially, I need to, as a disclaimer, of course, the WISE photometry only begins long after the flares occurred, so we're not seeing the early time behavior. But all of these colors were initially in the region that you could consider to be AGN-like, and as time has progressed and the flares evolved, they have declined more. Actually, most objects are still in the process of declining to quiescence. We just don't see the original quiescent value yet, because, well, we won't be able to confirm it because we didn't see any, we don't have any pre-flare mid-infrared. Whereas the AGN-like objects, those are the objects that show the coronal lines consistently and constantly, are kind of just acting like AGN you'd expect with some low-level variability in AGN-like colors. So the two populations of ECLEs can now, instead of referring to them as variable or non-variable, it's probably easier to refer to them as TDE ECLEs and AGN ECLEs. So just as a reminder, we're seeing the variability in the coronal lines and the diminishing of the coronal line signatures. And if any broad components were present in the hydrogen and helium features, those have now decayed as well. And there is also the issue that there was probably, because of the wide range of unconstrained phases, even the objects that didn't show broad hydrogen and helium features probably did earlier in their phase, we just don't see it. And in the mid-infrared behavior, there is both differences in their declines and their colors. And there's been no evidence of any of these objects, at least yet, rebrightening or having a second flare. And if you're interested, again, it's 5/7 of these objects were now in this class, and 2 of them are AGN, but don't take that as an estimate of the true population distribution. So now if we look at what will be going on the board as I think my favorite TDE is 18 DYK. This is its host galaxy. Again, it's not coming through very well there on the screen, but it's not a post-starburst galaxy either. It's star forming. And it's had a rather tumultuous classification history, I think it's fair to say. Yair originally classified it as a TDE, and then it was reclassified as a changing look liner, and then reclassified as a TDE based on its mid-infrared behavior and its late-time X-rays. It does actually pass Megan's cuts for the infrared TDE sample, as we saw earlier in the week, but it was excluded from the final gold sample based on this, which I think is fair. And it is also, I haven't mentioned it here, but it is also in Jason's sample of the ants as well, so the ambiguous nuclear transients. So what's going on? As a disclaimer to this is not yet published, and some of the plots are rather preliminary, but to give you an idea, I can take you through this. So this is the Atlas force photometry light curve, which does need to be cleaned up a little bit, but this is the original flare up here, and then that was seen to be declining, and then nothing has occurred since. It's essentially back to what it would be quiescently. And its spectral sequence, there are more spectra of this object than I'm showing here. These two were the ones that were easily accessible publicly for me when I was doing this. So I was interested because I'm trying to find more ECLEs at this point, and this object stood out to me because its DESI spectrum now looks like its SDSS spectrum quite quickly. So quickly being a relative term as far as these things go. But when it was actively in the TDE phase, it was showing the coronal lines. Not as strongly as the original ECLE sample, but so it kind of falls into this ambiguous territory, or perhaps a transitional object where there is coronal line activity certainly, but not to the same extent. And I will zoom in helpfully. So as you can see here, the iron 10 is present in these objects or this object that was in the spectrum that were taken near optical peak, but not to the same level, as I said, as the original ECLE sample. You see the broad TDE-like features in both the hydrogen alpha and H beta, And then similarly to the previous ECLEs, we're now seeing a development of the O3 line. And this is thought to, I should also say, it's that development of the O3 line is thought to be either a response to gas that's more distant to the actual event itself, or perhaps a combination of where this is, the continuum itself has now softened to the level that we're seeing lower ionization state lines. So, is it a liner AGN or is it something else? Thankfully, in the case of this object, we actually have a Mangas spectrum for the IFU data. This, its BBT diagnostic, especially in its core, is a mess, but which is not helpful by the fact that a lot of the BBT diagnostic lines in this object our object is quite faint, so it's hard to get good signal to noise. But when you look at it in the WAN diagram, which is specifically designed to help distinguish between liner emission coming from evolved stellar populations or as weak AGN, its core region, which is the region that we're most interested in, is coming from a retired galaxy population. So that's an evolved stellar population rather than being an AGN. And if we look at it for its mid-infrared, the rather large uncertainty is the gap between all-wise and neo-wise. That is not real, but it doesn't show any very much variability at all in the mid-infrared prior to its flare. And additionally, when you look at its in color space, from all-wise data, it is in the star-forming region. Then we see it's not certainly not as a strong flare as we've seen in the original ECLEs, but we see the same behavior where it has increased in or become redder in color and then declines. And like the ECLEs, we can also fit this with the power law. I'm not going to, I'll show the power law fits or the power law results shortly. But now, this is now comparing the mid-infrared behavior of this object to the original ECLE sample in gray, and a range of TDEs, perhaps your favorite is on here, that have now been observed to show coronal line activity at some stage in their evolution, but were classified as TDEs optically first. So if you can see here, I'm going to be able to reach at this point, but 18 DYK is, in color, as we see, it's following the same sort of trends, but it has a much shorter time scale. Whereas where the original ECLE sample have taken at least 20 years to reach their end of their decline, it's compressed in time scale and is less bright as well. We're also seeing that some of the optically selected TDEs are now showing very strong optical flares, but this is a case of where we have the early time data for those objects, we get the late time data for the original ECLE sample, and we now have a big observational gap where we don't know what happens in the middle. I'll just show the power law fits here as well, or power law results. So this is, I should also say, the SDSS J2220 object is an object that Joe found in his analysis of updated SDSS legacy spectra. And we think it might be an ECLE, but it doesn't necessarily behave in the same way, so we're a little unsure. But its power law, 18DYK's power law decline in the mid-infrared sits into the same range as the original ECLE, TDE ECLE sample. So that's consistent there, despite the difference in timescales. And then if you look at the flare brightness in both W1 and W2, if they were, this is a range of objects as well, which is the same as up there, we see that on a one-to-one relation, the ECLEs and the coronal line TDEs, as I'm calling them for the time being, don't sit in a one-to-one relation. This is 19AZH, which does show a very small mid-infrared flare, but no coronal line activity. So it's kind of here as a lower limit, kind of almost. And then if we look at it in color space, there is a lot of limits on this plot, and the trend line, the fit line is only to a few objects. So the fit line is to AZH, 18DYK, and 17GGE, as those are the only objects for which we see both the flare color turnover. GGE has much delayed flare turnover, but as also all these objects are now on the decline. Whereas for some of these objects as well, whilst we're seeing the flares reach their peak, the color hasn't necessarily reached its maximum. But when you compare the maximum difference from quiescence, which is still a little bit uncertain for some of the objects as well, to their maximal color, we see a relation where the brighter the flare in W2, the redder the flare. So there's a color and luminosity relation that's perhaps related to some ongoing, some structure, whether that is the covering factor or the material, the density, or the viewing angle effect. There's perhaps something there. But we do need, for this to be reliable, obviously, we do need more objects that aren't limits. So finding more coronal line TDEs and getting them observed at later times would be very interesting. So to finish off, there's some outstanding questions. There's still a big question on exactly how rare ECLE properties are, because there's a wide range in timescales where these coronal line features have developed. We don't necessarily know when the original sample began to show coronal lines. We just know that they persist for a few years, or up to a couple of decades in some. And then, so we're trying to find more of these through a combination of long-term follow-up of TDE samples in general, so seeing whether a few years after peak do they now develop coronal lines. And that's motivated by the fact that some of the new coronal line TDEs have showed coronal lines very close to optical peak, but something that GGE only displayed coronal lines after an X-ray flare nearly a year after its optical peak. We're conducting this through archival searches of both updated SDSS, this is the SDSS DR17, and that includes EBOS, which wasn't included in the original sample, and then with DESI. And then also using a live search of DESI. So this is the dark energy spectroscopic instrument, for those of you not aware. It's primarily a cosmology survey, but as part of that, it's obtaining millions of spectra of galaxies, and we're hoping to look through these as they come in to identify the objects and follow them up in near real time. And then there's also the question of if there's a proportion of these objects that are AGN that are showing very strong coronal lines, what makes them special compared to normal AGN that show coronal lines where the strength is much higher? That's still an open question. It could well be this is just we're seeing the top tail end of the continuum. We need more objects to confirm that. And the physical properties, so we're already seeing a range of time scales, coronal line emission strengths and coronal line emission ratios. So is this related to the circumnuclear material itself? Is that a density effect, or is it some viewing angle or geometry effect? And I think has been harped on enough in this conference this week, I'll do it again. Multi-wavelength observations of TDEs in general and at multi-epochs are really important, because just constraining yourself to 1 or 2 wavelength bands and 1 or 2 observations, I don't think will be enough to fully understand these objects going forward. So I will leave my summary slides up. And this is a link to my paper on the original ECLE follow-up and Joe's paper on the new search of the SDSS and the updated rate calculations. And I'm happy to take any questions.
Okay, questions?
I kind of asked you this at lunch, but I'm going to make you tell the room. Absent broad helium lines in one of these spectra, how can you say it's a TDE, even if it might not be like the other ones that we do know are more likely AGN? That is the problem with this at the minute. The only real way that we've been able to say is to look at it and see its variability later with time, because it's kind of at the minute, the best we can do is a comparative analysis. So the mid-infrared helps because their behavior are so different, but obviously that takes time to build this data set up. And we're also going to lose WISE to the upper atmosphere in about a year and a half, so that won't be very helpful after that. But for the moment, the idea is then we are doing some analysis where we hope to build up spectral templates. So essentially getting multiple observations of the ECLEs at different phases, so then you can compare that the same way that you could identify a supernova, because there is, it's very preliminary, but I do have a backup slide, where if you take, if you compare all the ECLE sample and split them into TDE ECLE and AGN ECLE from the SDSS, so these are various phases, there is potential evidence that some of the coronal line ratios between the groups are different, but that falls into the trap that you're then not really looking at the phases equally. So this could be, it could easily be after those coronal lines start to fade in the TDE ECLE, you can't really tell them apart. So multiple observation, I think, for the time being is the best way forward.
Great talk. I was wondering if you could comment a little bit on the line profiles of both the coronal lines and the broad Balmer lines. Do you see redshifts, blue shifts, asymmetries?
Not consistently. So the coronal lines tend to be pretty much at 0 redshift or small that. And we did see in the follow-up spectra that there was some variation in the hydrogen alpha. For example, it wiggled backwards and forwards, but it wasn't seen equally across all objects. And it wasn't consistent. It kind of redshifted or blue shifted one way and then went back then at the next observation. Again, I will say that's probably worth investigating at a higher cadence where we're not dealing with spectra that are like 10 years apart. But yes, for sure, that would be an interesting, because that might be a way to explore the dynamics of the gas that's nearby.
Thanks.
I was just interested in the timing, actually. So, I mean, the way, if you got these responses for 20 years, does that mean it's actually a 20-year deep amount of matter which is actually responding? Or is it a 5-year flare in 15 years, or can you actually deconvolve it?
I'm not sure we can deconvolve it fully at the moment because we just don't have the full timescale of what the early flares look like. There's for example, I'll bring this back because we don't have, for the original sample, all of these spectra are taken well after the initial phase. We don't even know what the original flare looked like in a lot of cases. One of them, the 05 or the 0952, did have an optical flare, but it was quite weak. So maybe it's an indication that there's perhaps these are quite obscured or something like that. But it would be hard to tell, I think, from what we have at the minute, because we are so limited in cadence, for example, and then resolution as well. It's kind of hard to. But I think with the current sample of TDEs that are now being selected that are developing coronal lines, where those are much higher cadence observations, and then we can see from there and work these out. Because I imagine that quite a lot of those will look, if we take observations in a couple of years, will look like this kind of spectral sequence. Where the broad features have faded away, and then we're just left with the coronal lines.
All right, thanks.
Do you have these coronal lines and O3 lines and other narrow lines equivalent with, meaning their total energy as a function of time? So you mean with, let's say, 4 epochs?
That's not something I did in my analysis currently, but that's something I would like to revisit, certainly, yes.
Yeah,
and see how those compare.
And then theorists, maybe in the room, can go ahead and then try to fit some models with those. So you mentioned that your O3 line is always increasing. Is that always the case? Even 20 years ago, 20 years later, it's still increasing?
Yes, so that it's not necessarily clear in all objects. This is where even though we have such a limited sample, there is significant variability across the sample. This is the largest example where this is very drastically increased, whereas 0952, it's more or less constant. So it's not the same in all the objects as well. So that would be worth investigating exactly why that's seen.
Yeah, exactly.
There is, I should also say, there is a little bit of variation between the SDSS and follow-up spectra, because you're not viewing exactly the same portion of the galaxy, because the fibers are slightly different sizes, and the long slit is not exploring exactly the same population. But I don't think anything to do with the fiber size or can explain that that is definitely a real evolution. So
yeah, if you can plot the equivalent width of that line as a function of time, then there's some story maybe one can tell. But looking at this, it's hard to say how much matter is there.
Yep.
Yeah. Thanks.
Yeah, thanks for the nice talk. I had a question about the AGM cut, or maybe it's actually a remark, but because I guess the reason that the AGM have those colors is because the dust is hot, but the same happens in an echo, right? So and you can see that because early on they are all in the AGN region, but it doesn't mean that they're AGN. So
exactly, that's why it's really great to see actually with the TDEs that we're seeing them rise up to this now and then fading off. So it's more that obviously we don't know what these objects were like beforehand, and it's great to see that it's not just enough to say, for example, that just because something looks like we catch it and it happens to look like an AGN color, that's not enough. It's the variability and evolution as well that plays a role in that, yes, for sure.
Yeah, and the increase in the oxygen tree is it's very exciting. Of course, with the more classical TDEs, we occasionally take a spectrum, but we've never seen that. So I guess it would still be a selection effect that you are finding these in gas-rich environments.
Yep.
But I think it would still be fun to see if you can get a handle on the energetics, maybe borrowing AGN scaling relations between O3 and X-ray.
Yep, that would be. It's certainly something to revisit, especially now that we're finding more. So, and I know that even seeing in DYK that even though this was an optically selected TDE, if you're prepared to accept that classification, and it's showing it as well. So it is certainly not just a one-off. So that's again very exciting. Yeah.
Ricardo?
Hi. Is there any difference in the manga data between the AGN or TDE CLEs in terms of where the iron lines are, especially?
Unfortunately, this is the only one of the original sample or the current sample that actually has manga data, at least for the time being, so I can't really comment on that further. Okay. But yes, it would be nice if anyone has IFU data of their TDE host lying about, that would be great to compare to. Yeah.
Any last questions? All right, let's thank Peter again.